right, make sure those cell phones are away. Here we go. Page 356. All right. All right, problem 1 through 4. So find the inverse of each of the relations. Okay, now let's make all terminology correct. Find the inverse of the relation. If it's a relation, does it have to be a function?
No.
No. So all you're going to do on problem number 1, 2, 3, and 4 is you're just going to flip-flop the x and y of everything. Okay? It just says find the inverse of the relation. So inverse of relation, you just flip-flop x and y. That's all you have to do. 5 through 7. Find the equation of the inverse relation. So number 5, we have this. Number 7, we have this. And number 10, we have this. So what was the first thing we had to do in order to start finding the inverse of the relation? Switch what? Yeah.
X and Y.
Switch x and y. So the first one's pretty simple. Switch x and y. Theoretically, that's the inverse, but then they want you to solve for y. So that's going to be y equals x plus 5 over 4. Okay? Problem 7. Should we start with the same thing? Flip-flop x and y? Sounds good to me. I'm going to make that y to the third x equals negative 5. Then I'm going to solve for, excuse me, y. So that's going to give me y to the third equals negative 5 over x. And then I'm going to take the third root of each side. So y equals the third root of negative 5 over x. Can you have a negative as a third root? Absolutely. Number 10, again, flip-flop x and y. You get, oops, yep, that'll work. Oh, call it good. You flip-flop x and y, and you automatically get the inverse because you just solve for y. So that's up to number 10. And then we had 17 through 31 odd. So a couple of you, I know you had some questions about this, says, given the function f, prove that f is 1-to-1 using the definition of 1-to-1 function on page 350. So let's just verify what 1-to-1 meant. Okay, it says, we see that the inverse, 1-to-1. A 1-to-1 function f is 1-to-1 if different inputs have different outputs. That is, that none of your a values equal b values, so the function of a is not equal to the function of b, or a function f is 1-to-1 if the outputs are the same, the inputs are the same, that is, function of a equals function of b, and a is equal to b. So if they're equal to each other, they're 1-to-1. So all of your inputs, long and short, what they're saying is, if you had an XY table, you had A, B, C, D, you had W, X, Y, Z. If none of these are equal to none of these, or if none of these match up in this row, none of them match up in this row, it's 1-to-1. Okay, so you don't have 3, 5, 3, 6, 4, 5, 4, 6. Nothing matches up. Hey, how you doing? Thank you for the little. Perfect. Good thing is, you're still in my class. I don't know what the rest means. So let's take a look at the functions and see what they do. So 17, we have function of x is equal to 1/3 x minus 6. What I would look at on this is, what does this graph look like if I had graphed it? Straight line. Okay, so if it's just a regular straight line, the inverse I'd say is going to be 1-to-1. Why do I know that? Because when you graph this, you have -6, and and then up 1, right 3. Pretty sure that if you found the inverse, it would be symmetric about the line y equals x. Okay? Nothing special about it. Then we go to 19. Some of these are going to start getting goofy on me. 19, function at x is equal to x to the third plus 1/2. First thing you should know is, what does x to the third as a graph look like? Well, if it's up here at half, it's shifted up half. And that's what the x to the third graph would look like. Do you think that if I had this line drawn here, my inverse would probably look something like this? I don't know, something like that. I can do that better. Something like that. The answer is yes. So if it's x to the third and hasn't done anything real special, I'm sure it's going to be 1-to-1. 21 says, given the function g, prove that g is not 1-to-1 using the definition of 1-to-1. Okay, so problem number 21, we have g at x is equal to 1 minus x squared, so we're proving these are not. What kind of shape is this if we graph it? Parabola. Parabola doing what? Opening down. So it has a y-intercept here, and it's doing this. Which test is this not going to pass? Horizontal line test. Okay, remember the vertical line test determines if it's a function. Horizontal line test, if you can draw a horizontal line that touches it twice or more, the 1-to-1 does not work for us. 23, we have g at x is equal to x to the fourth minus x squared. Okay, x to the fourth is going to be something like this. Okay, remember end behavior asymptotes is going to look like this. So again, this is not going to pass the horizontal line test. It doesn't pass the horizontal line test. It does not have an inverse function. Okay, the only time it would have an inverse function is if you restrict the domain. Okay. 25 is just an exponential function. All of your x values, all your y values are all going to be different. It passes the horizontal line test, so it is 1-to-1. 27 is not 1-to-1 because it's a parabola. It does not pass the horizontal line test. 29 would not pass the horizontal line test, so it's not 1-to-1. Excuse me. 31, the horizontal line test, if it's drawing a horizontal line, will touch it once. So it does, so that is 1-to-1. Then we went all the way to 61, is that right? I'm ripping the page. Do what? What? Okay, so 61 through 65. We want to match. It says find the inverse by thinking about the operations of the function, then reversing or undoing them. Check your work algebraically. So we're kind of matching up. Why I look at it on this is I can make this, change, taking it out of functional notation, then do this. And my inverse is going to be y equals x over 3, which again you could say function at x is equal to x over 3. That's your inverse. This one, I'm going to go y equals negative x, flip-flop x and y. X equals negative y, so y equals negative x. So you could write that as function at x is equal to negative x. There's your inverse. And then last one. Oops, got that. Flip-flop x and y. Cube both sides. So I get y equals x to the third plus 5. 68 through 72. Let's see. Each graph from 67 to 72 is graphed as 1 to 1. Sketch the graph of the inverse function. So I'm going to write down what all my points were first. So they're claiming we can easily find the inverse of this. So I'm going to plot 5, 2. Oh my gosh, I can't believe I did that. So this 2, 5 should have been up here. This should have been here. Why is my eraser not working? 2, 5. All right, so then I'm going to plot 5, 2, 1, 2, 3, 4, 5, 2. Those are inverses 3, 1, 2, 3, 1. Inverses 2, negative 4. And then negative 3, negative 6. So the red is the original, the green is the inverse. You should see that it's symmetric about that line if I drew it right. Verifies its inverse. We're going to do the same for number 70. And we'll do the same for number 72. Number 72, you're obviously going to have to find 2 points that work with that linear equation. Then 80 through 86. Find the inverse of the given one-to-one function, f. Give the domain and the range of f and f at negative 1. And then graph both f and f at negative 1 on the same set of axes. So 80, I have this. So I have what is the domain of the original? Yep, negative, positive, infinity. What's the range? Same. Let's find the inverse. So I have y equals 2 minus x, flip-flop x and y. Solve for y. We got plus 2. And then same thing. Down one, right one. Is that symmetric about that line? The answer is yes. It's a horrible picture of that line, but it happens to be the same thing. So obviously they're 1 to 1 if they're the exact same thing. 82. Oh. What's the domain and range of the, let me push your phone away, please. What's the domain and range of the inverse? Yeah, same exact thing. Same line, so the domain and range are going to be the same. So this will also be the domain and range. 82. Hey, how are you?
Good, thanks. How are you?
Yeah, well, thank you. Scotty. Uh-oh. Such your ballerina outfit is in. number 82, we have this. What do you think the domain of this would be? Good. Negative infinity, -1. -1 to infinity. Range, any ideas? Negative to positive infinity, I'd go with. Now, I argued with a teacher for a whole semester, which I know sounds like the most exciting thing on earth is arguing with a teacher about math. She kept saying, hey, all you have to do in order to find the inverse is you just flip-flop domain and range. And it's the most incorrect statement you can say because the one-to-one doesn't exist in that case. So is there a number value that is restricting our domain and our range right now? -1. So -1 has to restrict our domain of the inverse even if it doesn't look like it. Say that one last time. We are restricted by -1 right now of our domain. So our domain of our inverse has to have -1 as a restriction at the least. It can have more, but it also has to have -1. So if I were to graph this using the calculator, I'd probably use a t-table because I can't see it right away. And I might go -2, -1, 0, 1, and 2. Plugging the values in quickly. -2 plus 1 is -1. 3 over -1 is -3. -3 gives me +3, so I'm going to get -2, +3. This is not going to work. It's got to be an asymptote. Plug 0 in. I'm going to get -3 out. If I plug 1 in, I'm going to get -3/2, which is -1.5. So 1, -1.5. And then if I plug 2 in, I'm going to get 2 plus 1, which is 3. -3 over 3 is -1. So 2, -1. So this graph is going to probably look something like this, and then like this. And I guess we would also have this as a asymptote. So will we have symmetry? Possibly. Let's find the inverse of it. Okay. What is our restriction in the domain of the red? I have -3 over x minus 1. What is my restriction? 0. But with that known, I know that 0 is not going to work here. What else can I not use? I said it earlier. I can't use -1. So -1 also won't work. The reason it won't work is because it was restricted originally. Okay? And then if you go through and you plot that, so that's basically what your graph. This graph is actually going to look like this. It will actually have a hole. It's going to do this and like this. It's going to have a hole right there, though. That's where your restricted value is. And that's how you get your domain range. And I'm done. Hand those in, please. All right, I'm teaching now. Starting to record, so you guys got to be behaving. For those kids that are from the old school who watch my videos that were...
They really still do that?
I don't know. Use your calculator to sketch these graphs in the standard window. Okay? So...
No, she can't.
Walker, turn around and get rude. Don't make me call your mom. Alright, shh. We want to graph this on a graphing calculator. So, in your graphing calculator, you would plug it in as y, and then you have 2 to the caret x. This is called an exponential function. I would say you could easily just make a t-table, figure it out. 2 to the negative 2 power is the same thing as what? No. 1 over 2. 1 over 2.
Like that, squared.
1 over 2 squared, which is 1 over 4. And then this one is 2 to the negative 1, which is 1 over 2. What is 2 to the 0 power? 1. Good. 2 to the first is 2. 2 to the second is 4. That's a 4. I know. Yeah, squint. All right, negative 2, and then 1/4 is like right here. Negative 1, 1/2 is up a little bit higher. It's twice as high. 0, 1. 1 and 2, and then 2 and 4. So this graph is doing this. Exponential functions. This is how things in life grow. This is how the cells in your body grow. They grow exponentially. This is how you want your money to grow if you're investing correctly. Unfortunately, 8 years ago, it took a little dip. Okay? And unfortunately, it kind of goofed up some people's portfolios. I feel I was kind of fortunate at the time because I was not retired. So if my portfolio takes a dip and I'm still investing at that point, then it increases again. So think of it this way. If you go and buy a stock, and let's say you're buying the stock and it's $4 a share the whole time, and then you're investing $100 each time. So each time you're buying 25 shares of this because it's $4 a share at $100, and then it drops to $2 a share. What are you able to do with that $100 now? Are you buying more shares or less shares if it drops to $2 a share? You're able to buy more. And then if the stock recoups and goes back up to $4 a share, all those shares you bought at $2 a share are now worth $4 a share. So that period of time, you doubled your money, right? Now, the thing that stinks is, let's say you go and buy something. Let's say you go and buy Apple, okay? Apple just hit $800 a share. Pretty good. So let's say you bought a whole bunch of $800 a share. It drops to $500 a share the next week. You still own all those shares, but they're worth less money than they had been. So the wise thing is, if this is just kind of going through as investing at a low end. If you go slow and steady and invest slow and steady throughout the time from when you're working age till you retire, the market's going to go up and it's going to go down. The bad thing is, anytime you look at a newspaper, if they want to make it look dramatic, they're going to focus on a little tiny portion of the stock market. Going, look, this is the worst it's ever been. No, the worst it's ever been is started at 0. And it's not going to go negative. So if the market's, if you look at the whole thing of the market, is actually an exponential function for the most part. But what newspapers and analysts will do is like, let's take a look at this window right here. So you're not looking at the whole graph. But then inside this window, you realize that the graph did this. And they're like, no, look at how bad that is. It went down there. But if you looked at the whole graph, it went up. This is time. Times. Okay, because I'm grammatically correct sometimes. But that's what you have to care when you're looking at stuff. A lot of people are like, oh my gosh, let's focus on this one little portion of a whole system of events. And if you're the person saying, okay, I am age 60, and I'm going to save from age 60 to 65, you're in trouble. If you're like, okay, I am out of college now, I'm 25 years old, I'm starting my new job, my new career, my 23, whatever age you are, you're starting your new career, you start saving, and you work for the next 40 years, in that 40 years of time, 40 years could go from here to here. What happened in that region in that 40 years? It went up. What happens if I micromanage a small little portion? I can make it look real bad. And unfortunately, that's what they do. You ever watch that Kramer guy? I know you guys have probably watched. He's that bald guy. No, Kramer. He's a stock analyst, and he sits there and he like screams at the camera the whole time, telling you how right he was or how wrong he was, depending upon the day. Don't watch it. The only reason I watch it is sometimes he's on at the gym, when I'm on one of the cardio things. And so it's like, rather than watching CNN, because I hate CNN, and all the old people love it, and they, let's watch CNN all day long. I'm like, oh my gosh, no. Let's put on like, Cops or something. Yeah. I need something to get me going when I'm working out. I don't need to watch CNN going, oh, look at all these poor people. Okay, and then you watch Kramer going, yeah, bam, look what happened, bam. And you're like, wait, you're not, you're not the cook, you're not doing this stuff. But they always focus on those small, little, minute portion. If I were to ask you all this, you all are probably overall pretty good drivers. How do I know that? Because if you're driving to school each day, you're making it each day. Therefore, I can conclude over your overall pattern of driving, and that you're here most days, that you're a good driver. Could I follow you and micromanage your driving and say, oh, you wove out of your lane right there? And then I focus on that, saying, look how bad of a driver you are. Would a 100-foot span in your driving from here to your home over the course of your lifetime, if I looked at one little 100 yards and nitpicked it, does that mean you're a bad driver? So don't look at the micromanaged portion of anything. Okay? I know you've all gotten in trouble, or your brothers and sisters have gotten in trouble, or your brothers and sisters have gotten you into trouble. First thing you tattle on it as your little brother, if you're the little brother or little sister, is, Mom, so-and-so hit me. Right? You guys heard that? Is that the whole truth? Luke, you're the youngest of four, right? Yeah. How many times did brothers hit you? Were you innocent the whole time? You never antagonized, like they just came over to you and wailed on you. Okay, so with the mom, so-and-so hit me, was, yes, they did hit you, but the whole truth of the matter was? There you go. Two kids get in a fight. Two kids in the fight. You know which kid is glad the fight's getting broken up? The kid getting thumped. You two coming through, thank God I'm not getting beat up anymore. Right? So then you're going to talk to both kids. Okay, so what happened? Oh, I just came over and started punching me for no reason. So what happened? You ran over my dog, punched my sister in the face, and flipped my mom off. Well, I guess I did that. Bad words on here. So, again, watch out for these kind of graphs. And the reason I went on that little tangent was, one, it's kind of fun to talk about, but two, realize exponential functions are easy to deal with. Unfortunately, they are misconstrued too often. Okay. Is this function increasing or decreasing? Increasing? Is this function increasing or decreasing? Decreasing? Is this function increasing or decreasing? Decreasing? And then, what about this function? Increasing. Okay, so increasing, decreasing is going to take place. I think you have enough here to jump onto the assignment. Okay, so what I'm going to give you this. So you're going to have quite a few graphing. Page 370, 11 through 19 odd. 28 through 32 even.
Happy birthday! He's like, it's not my birthday.
Dude, are you kidding me?
Yes, no.
Baseball games, like, you'll just see him, you'll just see him, like, zoom in. Like, it'd be like a lot of his hands, like, He's an entire policy.
You know where that one's going. We're going to special folder.
He probably doesn't put
No, he has his own little weird folder.
Parker told me like what car is in Jack Joe? He thinks he's like the coolest car ever.
Yeah.
It's like this 3-door like
Little Volster.
Yeah. It's got 3 doors and he thinks it's like the coolest car.
Yeah, he loves it. He loves it, dude. No, it has 4 doors. It'd be weird if it had 3 doors. Like, on baseball trips, you like take us to a movie.
Yeah, that's his
Safer. Love Jackson shots.
He puts up like 1,000 pictures for every football.
Same thing for every single summer.
All right, so 370, 11 through 19 odd, 28, 32 even, 33, 35, 36. If you graph any of those that they ask you to graph, make sure you state the domain and range of what you have graphed. Sound good? All I got for you. Got 5 minutes left. What should we talk about?